Hi everyone, this is Shao-Chuan. I'm going to present the homework 2, probability and stochastic, problem 2. The y-sense stationary process. If its mean is constant and its autocorrelation is a function of time difference. The WSS only uses mean and autocorrelation. In practice, they are much easier to get than second-order density. Based on the mean and the autocorrelation function, we can do many things already. We can do state estimation, parameter estimation, and prediction. In mean-square sense, in communication application, in most cases, we do not care too much on a specific value of the stochastic process. We pay our concentration on the power of the signal. The autocorrelation function is the average power of the signal that at T1. We see that when the input is WSS process, the output of the stable LTI system is also WSS. Independent increment process means the x of T1 minus x of T2 and x of T3 minus x of T4 on non-overlapping intervals are independent. So far, we see that Poisson process, random walk, and Wiener process are independent increment process. It seems independent increment property is somehow related to Markov process. The Markov process is that if the past has no influence on the future, when the present is none. So far, we see that Poisson process, Poisson impulse, semi-random telegraph, random walk, and Wiener process are all Markov process. In the real world, many processes have Markov property. The binary transmission in early homework is the discrete state Markov process. In that sense, we call it a Markov chain. The normal process is the process that the x of t is said to be normal if the random variable are jointly normal for any n, any t1, t2, and tn. That is, the f of x is equal to this formula shown here. Discussion: the statistics of the normal process is completely determined in terms of its mean, lambda of t, and autocorrelation of t1, t2. In general, epsilon t of t is a function of t. In this course, we classify the Wiener process as one example of a stochastic process, and we classify the normal process as a property of stochastic process. That is, we treat normal process as a large class of stochastic process and treat Wiener process as a specific example. The strict sense stationary process, if its statistic is not affected by a shift on the time axis, the SS process requires f of x. This condition is very hard to meet. The white noise. For Wiener process, if we wish to discuss its derivative v of t, we have expectation of v of t is equal to 0, and autocorrelation is equal to alpha lambda of t1 minus t2. The Wiener process does have derivative. We use the v of t just as a notation. When we need further discussion, instead of v of t dt, we use derivative d of omega t. The omega t is continuous with probability 1. It has differential d of omega t, and the v of t is the V of t is Gaussian white noise with zero mean and impulse autocorrelation function. We wish to define more general white noise with zero mean and impulse autocorrelation function. A stochastic process is said to be a white noise if the expectation of V of t is equal to 0 and autocorrelation is equal to this formula shown here. The mean ergodic process, if the limitation is the mean square sense. In mean square sense is one kind of consistency. There are others in probability with probability 1. In this course, we discuss in mean square sense only.